So welcome everybody to the morning session of the second day. First speaker of today is Romain Petrides, and he will speak about geometric spectral optimization on surfaces. Please.
Okay, so thank you for the invitation in this conference. I'm really happy to be here in Brazil and here to discover new topics for me. The goal here is to talk about optimization of eigenvalues. So in some sense, I will continue the talk by Misha yesterday. My talk will be maybe more analytic than geometric, so it will be complementary to Misha's talk. So when I finished the preparation of this presentation, I figured out that it is I have many things to tell, so if I do not go in until the end, it's fine. I'll be as slow as possible. So let's start with the beginning, with the variational problem. So we are on a closed connected surface, which is also so closed, it is compact, endowed with a Riemannian metric in dimension 2. With a metric, we can define a Laplacian, and we can define eigenvalues associated to this Laplacian, so associated to the Riemannian metric. So I define the eigenvalues like this. It's just the diagonalization of the Laplacian. So you have a min-max formula with respect to a Rayleigh quotient. And here my min-max formula is formulated in terms of infimum over spaces which are on dimension k plus 1 of the maximum of function in these spaces of the Rayleigh quotient. So why k plus 1 instead of k? It's to tell that the first eigenvalue is non-zero on a connected surface. So remember that the constant function is an eigenfunction for eigenvalues. If you take a surface which is non-connected, you can have this constant function on one part and 0 on the other. It is one eigenfunction, and we have another eigenfunction here. And the first eigenvalue in that sense is equal to 0. But if you take a connected surface, the only function associated to 0 are the constant functions. So we do not want this function to appear. You can put another formula, which is the infimum over spaces of dimension k plus 1 of functions which are orthogonal to the constant function. It's another way to set the problem. Okay, so I wanted to give you this formula because it's important in spectral geometry. We'll see soon. So this is the case eigenvalue, and we would like to optimize it with respect to the metric. So as for the systole, you have to renormalize it. So the good renormalization is by multiplication of the area with respect to the metric. So this is the case renormalized eigenvalue associated to the metric. And we would like to study variational problems associated to this kind of functional. From the metric, I associate lambda k, and also combinations of them. So for the presentation, I will focus on the first one, but combination of them could be done in this context too. So this, you set lambda 1 of sigma, which is a topological invariance, as the supremum overall of the metric of the first non-zero eigenvalue on the surface. Okay, so why the supremum first? So it's a classical argument in spectral geometry. If you look for the infimum over metric of lambda 1 bar, so as Misha told you yesterday, when you are interested in this problem, we'll see that you obtain, if you obtain a maximizer, you obtain a minimal surface. More generally, critical points of this functional are associated to minimal surfaces. So one motivation is to look for critical metric for that and obtain minimal surfaces. the best way to have critical points is to look for maxima or minima. So that's why I just talk about minimization. And OK, the infimum over all the metric is always 0. So it is not realized because lambda 1 is positive. And the way to prove that is to make this drawing, which is somewhat an approximation of this drawing. You take disconnected surfaces and you connect them with a very thin cylinder. And you use this test function with a kind of linear thing that has a small gradient here, so that a set of metric G epsilon associated to this surface has first eigenvalue going to 0. OK, so maximization is the only relevant thing to do if you want to optimize it. So I retalk about the historical result about optimization of eigenvalues. So there is the first result by Hersch on spheres, which tells you that the first eigenvalue is the maximum is 8 pi. And it is only realized by the round sphere. And Misha told you about the eigenfunction on the round sphere, the coordinate functions. And the way to prove this is just a test function thing. So you have a lambda 1, which is defined as an infimum of the Rayleigh quotient. And you test the coordinate function on the sphere to prove that the coordinate functions are the best one in order to have 8 pi. This is coarsely the argument of Hersch. And yeah, we can refine this argument to have this kind of inequality, which is a generalization. OK. Then computation in the 70s proved that the flat equilateral torus is the maximizers among flat tori, and he made a conjecture that was proved later, which is that the flat equilateral torus is in fact a maximizer of the first eigenvalue on tori. So since the result was solved in the sphere, he was interested in the following topological thing, surfaces of genus 1, and then you can continue. Yang and Yao proved that if you have an orientable surface, in fact, lambda 1 is finite over all the metric. So you have a refinement of Hersch arguments on any surface of any genus. So this proves that the functional the supremum is finite, so that it's a good signal that you can do maximization. Then you have an explicit result for the hyperbolic plane. Also, for any k, you have a bound, which depends only on the index of the eigenvalue and the genus of the surface. And finally, in my story, Nadirashvili proved that the flat equilateral torus is the maximizer for the first eigenvalue on torus. So what's interesting in Nadirashvili's result is, OK, you have a maximizer, but you also have, a kind of method that is suggested. And it's suggested by this theorem that Misha told you yesterday, but in the geometric point of view. I will focus on the analytic point of view for this presentation. If G is critical for lambda 1, so what does it mean critical? Because lambda 1, so critical is like you want the differential to be equal to 0. But for lambda 1, it's not a C1 functional, because if you take a metric G, and for instance, you take directional derivative with respect to H, which is a 2-0 symmetric tensor, which is a tangent plane of metric space, then your set of, your graph of eigenvalues is like this. So you have t equals 0, for instance, and you can, have branches of eigenvalues. like this. But the way I put the indices of eigenvalues is, okay, you take the minimal one, which is lambda 1. The following one is lambda 2, it is there, lambda 3, etc. But in this graph, you see that lambda 1 cannot be a C1 function. It cannot be, cannot have derivative here. So criticality has to be written in another meaning. And the definition of criticality is for any variation, so for any h and any variation, the left and right derivative have a different sign for any variation. So that's the definition of Nadirashvili. And in that sense, he proved that if G is critical for lambda 1, then you have a family of eigenfunctions that create a map into RP. So they are eigenfunctions. It's the first condition here. But they satisfy a sum of phi I squared equal to 1. So they are the map phi is into the sphere, the Euclidean sphere. And they satisfy this condition. So this is a criticality condition, and just geometric interpretation that was explained by Misha yesterday is that if you take both 1 and 2, then you obtain a harmonic map into the sphere, which is a critical point of the Dirichlet energy among maps that are into the sphere. 3 implies that phi is conformal, so it's just the equation for conformality. And if you take 1, 2, and 3, both of them, all of these conditions, you obtain minimal immersion into some sphere. And you also obtain that the metric is just the pullback of the Euclidean metric on the sphere. Okay, so this is the geometric interpretation, but here what I see is just PDEs. So I'll explain you what are hidden with these PDEs. So to complete, I mean, what Misha told you yesterday, I just give you many examples of computation of critical metrics for other operators, for higher dimension. So Laplacian has the critical metric for the Laplacian are associated to minimal immersion into spheres, and it's also true in a higher dimension. For Steklov eigenvalue, it's free boundary minimal surfaces. You also have critical metrics characterization for eigenvalues of the conformal Laplacian, of the Dirac eigenvalue, combinations of Laplace and Steklov eigenvalues. So instead of having a sphere as a target manifold, you have an ellipsoid whose parameters are associated to, are the eigenvalues associated to critical metrics. Panite's eigenvalues, etc., etc. Okay, so you have an industry of computations of critical metrics, and it's a motivation to make spectral optimization in order to construct solution of these things, which are, I mean, kind of geometric interpretation of critical metrics. Okay, so I just give 2 geometric examples of results by spectral optimization. So I prove the existence of free boundary minimal disks into ellipsoids, which are non-planar. So let me explain. You can think about the geodesics, the problem of geodesics. You take an ellipsoid, and you know that on the ellipsoid you have planar geodesics, 3 planar geodesics. This one, and the one in the plane of the blackboard. And the question could be, do you have other embedded geodesics in your ellipsoid? So the result is yes. It's a result given in the 70s. I do not remember who did that. But you can have it if the ellipsoid is sufficiently elongated. So if you have a sphere, it's not possible to do that, of course. you have a similar question with free boundary minimal disks, in fact. So the question is, can we obtain free boundary minimal disks, so surfaces which are minimal inside that hit the boundary orthogonally, which have the topology of the disk. So of course, you also have these disks, these planar disks as free boundary minimal surfaces. The question could be, do you have other disks? And the answer is yes. And this result can be proved by a spectral optimization. So in this case, you use that the critical metric associated to combinations of eigenvalues are minimal surfaces into ellipsoids. So here it's by maximization of the first and second Sekloff eigenvalues. So it's equivalent optimization for, I mean, the same reasons are as Misha told you yesterday, in order to have embeddedness. And the surfaces I constructed resembles to, I mean, to something like this. It's like, okay, I put the trace on the boundary of my surface, and I have like two disks that are connected by a kind of half catenoid here. So that's the kind of solution you have for sufficiently elongated ellipsoids. Okay, so it's an indirect method to construct minimal surfaces. And also, I mentioned the result of yesterday by Karpukhin, Kussner, McGrath, and Stern, KKMS in the following, that proved the existence of free boundary minimal surfaces into spheres of any topology by optimization of the first Sekloff eigenvalues. Okay, it's geometric motivation to do spectral optimization here. So let's go back to our original problem. Do we have a maximizer? The answer is yes. So for any orientable surface, sigma, lambda 1 of sigma, which is the supremum over all the metrics of the renormalized eigenvalue, realizes its maximum. And the maximum is realized at smooth metrics except on conical singularities. So let me comment this result. It generalizes explicit results that were known before on the sphere by Hersch on the projective plane, as the torus, the Klein bottle, and surfaces, orientable surfaces of genus 2. It extends the result by KKMS that proved that among two consecutive orientable surface, I mean, two orientable surfaces of consecutive genus, you have existence. And also, I have to mention that conical singularities are natural in this problem because they appear as branch points of the minimal immersions. And this is optimal in the sense that the maximal metrics for orientable surfaces of genus 2 must have conical singularities. Okay, so let's start with the proof of these results, if there is no question at that point. So one first thing we do in this case, so it's classical in geometric analysis, is to restrict our problem to the conformal class of metrics. So here, lambda 1 of sigma is the supremum over all the metrics, and I split the optimization into optimization over the conformal classes of this invariant, which is a conformal invariant, lambda 1 of sigma g, which is a supremum over all the metrics in the conformal class. So why this is convenient? It is convenient to do that. It's because you transform your geometric problem into an analytic problem because you maximize on the set of functions. And I mean, you can use techniques in variational methods to maximize on sets of functions. But why this geometric thing is interesting to do? It's because you have a nice critical condition for optimizer in a conformal class. So it's again a result by Nadirashvili. So I renamed the functional lambda 1 as lambda 1 depending on the function, lambda 1 of beta. And if beta is critical for lambda 1, then we have those two conditions. So notice that compared to the other critical theorem, we do not have the third condition, which was conformality of the map, but we still have that the coordinate function are eigenfunctions associated with the first eigenvalue of the critical beta, and that phi, the map phi, is inside the sphere. So that's the critical condition in the sense of that. In any direction, the left and right derivative have different sign. So here it gives, if you compute this, it gives that beta depends on phi, which is the nabla phi squared over lambda. It's a kind of density of energy of your map. So you obtain harmonic maps. So let me write it here. So this is what I will call the Euler-Lagrange condition. And it's a PD. And I'm very happy with this PD. So this, in fact, implies that Laplace phi equals to nabla phi squared phi, phi squared equal to 1, and beta is written in terms of phi. And the first thing I would like to do is to study this critical condition, so this PD. So let me give you elements of analysis. So as I told you, harmonic maps into some sphere are critical points of the Dirichlet energy under the constraint that the map is into the sphere. And if you compute the Euler-Lagrange equation, it is this one. Okay, and you can do it in a weak sense. So you take your favorite variational space, which is the Sobolev H1, which is convenient for Dirichlet energy. And you can formulate this Euler-Lagrange equation in this space. And what we have is a regularity result. So if you take a map phi, which is a weak harmonic map, which satisfies this equation in a weak sense, so in the sense of distributions, then it is smooth. So it's the same result as for harmonic functions, for instance. So we can be very happy for that, with that, to make a variational method. Moreover, you have another property, which is like you have elliptic estimates. So elliptic estimates is maybe well known for you. If you have an equation like this, you know that, for instance, if f belongs to LP with p bigger than 1, then phi belongs to W2P. So you have you can have regularity and obtain two derivatives for phi. And if you assume that f is equal to nabla phi squared phi, then you can bootstrap the arguments and obtain that phi belongs to C infinity. And you also get estimates like this. The problem of this equation is well known. That nabla phi squared phi is not in LP, it is in L1, and you do not have elliptic estimates for, second term in L1. So that's a real result. It's not a classical elliptic result. You need to use the structure of the equation to prove that it is regular. And this is due to this kind of assumption I do here. I want the energy to be small in order to have elliptic estimates, which are true for classical equations, but not for this equation. So you need another assumption, which is nabla phi squared has to be small. You need small energy in order to have elliptic estimates. And this is called the epsilon regularity result. Well, how can I explain that to geometers? I can say that this kind of epsilon regularity result is really connected to uniqueness of solutions of harmonic maps with Dirichlet boundary conditions. If you have a small energy, then the solution is unique. And it's similar to the geodesic problem. If you know that you want a geodesic between 2 points, and if you know that the energy is small, then you have a unique solution. And wanting this uniqueness enforces you to have small energy in some sense. So this is a necessary assumption. Okay. And because of this epsilon regularity result, we obtain that with an extra assumption, the set of critical metrics, so the set of harmonic maps, is compact. So the extra assumption is this one. You need the first eigenvalue to be above a threshold. And this is a natural thing if you look at the epsilon regularity results. So take a sequence of such functions. And well, if you know that at any point the energy can be of this sequence can be as small as you want, then you have any elliptic estimates you want, and you converge. It is compact. The only thing that can happen is that you have a concentration of the energy on points. So you have your surface here, and imagine you have concentration of energy. Then your energy here converges to Dirac plus something else. Dirac over this point x, if you have concentration here, plus a measure here. And if you assume that this measure has a mass, and this has a mass, then you can do exactly the same argument as there, the Shiger-Dumble arguments, to tell that, okay, you have a test function here, a test function elsewhere, which is 1 here and 0 here. So 1 close to this point and 0 elsewhere, and you have something with small gradients, and also 1 and 0. You have two test functions for lambda 1 that give you that lambda 1 of this has to go to 0. But it's not possible if you assume this, that lambda 1 is bigger than 8 pi. Okay, there is the last thing, which is, so here the geometric drawing is like you have a surface, and you have something with blows here, and you have, a kind of disconnection that make lambda 1 go to 0. The last thing I have to assume is you have a Dirac at the limit, but no mass for this measure. And this gives you something like this with a big sphere that appears. And you obtain, test functions which are the one of Hersch, which are the coordinate function, in order to prove that the lambda 1 has to be less than 8 pi in some sense. So with this assumption, it's not possible to. So okay, it's compact. And okay, it was a bit technical to explain that, but just you can think that if you have a functional, your favorite functional, the systolic functional, and if you have an Euler-Lagrange condition that gives you that the set of critical metrics is compact, or even the subset of maximal metric is compact, then you can think of what follows, of arguments that follows. You can hope for a variational method. So here, it works in this case. If you assume that the first eigenvalue is bigger than 8 pi, it's okay. And this is okay. I proved in the theorem that you have this condition. that the supremum is bigger than 8 pi, if it is not a sphere, and this gives you a regularity result. So I shall explain you the methods that are hidden with this theorem. Just general things. So I used a kind of relaxation method to prove that originally. There is another relaxation method that was used after. There is a method by Karpukhin and Stern, which is a kind of indirect method associated to another characterization of the first eigenvalue. And I would like to explain you a new method, which is based on the construction of Palais-May-like maximizing sequence. So let me explain that. So if you know nothing in variational theory, you have a naive attempt to do when you have a functional and you want to maximize it or minimize it. So I recall the formula for this functional. First, you extend lambda 1 to a variational space, which is somewhat big, in order to have compactness of a maximizing sequence, for instance. So in general, it's like you want A to be a complete space or something like this. And it has to be adapted to the functional. Then you take a maximizer in this big variational space. It is possible to do that because, okay, you chose well A in order to have weak compactness of maximizing sequences in A. And you use a kind of continuity of the functional in this space. So you have a maximizer. Then you prove Euler-Lagrange condition on this maximizer, which is on a bigger space again. And because of this Euler-Lagrange condition, so I just explained in the blue lines what is the definition of Euler-Lagrange condition. So I just explain you with this drawing. And then you use regularity results on the Euler-Lagrange to prove that beta is smooth. So you use the regularity result of maps associated to beta, which are harmonic maps in the weak sense, so they are smooth. And then beta is connected to this smooth function, so beta is smooth. Sketch of proof. Okay, but you need to choose A. When you see this functional, the most adapted A is in fact the space of probability measures. So beta is not a, I mean, you look at beta DAG and you replace it by a probability measure. Because when you take a maximizing sequence, you can renormalize it. So you can be in the space of probability measures. So this can be generalized as a definition. You take the infimum over things, you replace beta DAG by a probability measure. This functional is, you are happy because it is upper semi-continuous by kind of definition, because you take an infimum and it's okay. You have weak compactness because the set of probability measure is the dual of the space of continuous function. So as a dual, you have the weak star convergence. So it weak star converges. So step 1 and 2 is okay. The problem is step 3. You want to formulate Euler-Lagrange equation associated to this measure, but it's not possible. You are not sure to have even have eigenfunctions, in fact, because you do not have the compact embedding of H1 into L2 associated to the measure. So it fails. But here it was the naive approach. We never used, almost never used the Euler-Lagrange equation. We would like, I mean, in this method, we use the Euler-Lagrange equation just in the end. But if you cannot formulate it, it's not possible. But you can try to formulate it before passing to the limit. So that's the heart of the idea of Eklund. So let's state the theorem of Eklund. You take a complete metric space. You take function on this space which is lower semi-continuous. So here we are very happy because our function will be upper semi-continuous, lambda 1. So we will apply this theorem to minus f, to minus lambda 1, sorry. And you take something which is almost a minimum. So almost up to a delta which is small. Then Eklund guarantees that you have something in A which is better than x, in the sense that it is less than, the f of y is less than f of x, so it's closer to the minimum. That the distance between x and y is small, controlled by the square root of the delta squared, so by delta, and that you have this. For any choice of another point in A, this difference is controlled. So let me focus on the third condition. And assume that A is a vector space. So A is a Banach space, in fact. And that F is a C1 functional. Then we obtain this condition. So it's just a rate of variation. Like you would like to compute, in fact, the derivative of f. And it is controlled by minus delta. So this gives you, by application, that the norm of the differential in the dual of A is small. As small as your choice is, your choice something close to the infimum. So a drawing we can do is the following one. Imagine your function is just a one-dimensional function. Imagine you want to approach the infimum, and your function does some kind of graph like this. You choose a minimizing sequence. So at the beginning, it's a bad minimizing sequence in some sense, in the sense that it is far from being critical, in the sense that the derivative is far from being equal to 0. And Eklund's variational principle gives you, because you are a minimizing sequence, it gives you a sequence that is very close to be also a critical sequence. So you obtain something which is close to this, but also close to be critical. So it gives you a compromise between being critical and being close to your initial minimizing sequence. So in this example, you can see that the function is C1. So it's very easy to construct it elementarily, but this gives you a theorem for any lower semi-continuous function, so it does not have to be C1, and for any complete space. So it's very strong. And so in this example, you can also see that a minimizing sequence will not converge. So you need another condition in order to have convergence, which is a compactness condition. If you know that the set of critical points is compact, that's what I told you about harmonic maps. Or if, the set of almost critical points are compact, it's also okay. And okay, that's called in the literature a Palais-Mail sequence. And we say that if Palais-Mail sequences are compact, we say that the functional satisfies the Palais-Mail condition. So it's well known, in fact, this thing. So what we would like to do for lambda 1 is to apply Eklund variational principle to a good choice of A, of the complete variational space. And to prove that if you are almost critical in that sense, you are, if you have an almost critical maximizing sequence, then it is compact, and you obtain a maximizer. So just I take the time to tell again what I just told you. So in our problem, we take an almost maximizer. We apply, we extend lambda 1 to a good variational space. But in blue, I just write that A has to be chosen such that you can compute a Lagrange equation for A. Because if you cannot, you are as in the first case. I mean, if you choose probability measure, you cannot formulate any almost a Lagrange equation, because before, even for the critical case, you cannot do it. So you have to choose A in a sense that is smaller than this A. You have to take a subspace of this. Okay? Then you apply your Eklund variational principle. So from your initial maximizing sequence, you construct a new maximizing sequence that almost satisfies the Euler-Lagrange equation. But there is a competition. So in the second step, I told you you have to restrict A in order to formulate a Euler-Lagrange equation. But you also have to have the bigger A you can have in order to have a sharper Euler-Lagrange condition. Because for C1 functionals, I told you that the small condition holds in the dual space of your thing. So in some sense, the bigger is A, the smaller is the dual space in some sense. Let me give you an example. If you choose LP, so here, you have EL. I can show that almost EL is something like this, okay, coarsely. Something like this. So if you choose A as LP for P bigger than 1, so if you choose A equal to L1, A star is equal to L infinity, so that you obtain an Euler-Lagrange condition which is in L infinity. This is very convenient for me if I have this. But again, if you take A equal to L1, this means that beta is in L1, and you cannot formulate any Euler-Lagrange equation for this. So it's too big, in the sense that the second condition cannot be satisfied. You cannot have a Euler-Lagrange condition if you choose A equal to L1. However, the fictive Euler-Lagrange condition you have is very good. Okay? So you have to reduce your L1. But if you choose A equal to LP for P bigger than 1, then it's okay. The Euler-Lagrange condition can be formulated because you have compactness of the embeddings and you can define the eigenfunctions and so on. This time, A star is equal to A P prime, but it's not L infinity. It can be a P prime very big, but not infinity. And that's not sufficient to make this sequence converge in some sense. So it's not as big as we want. And this space is not as small as we want in some sense. Okay. You would like to be very precise in the choice of A. That's the idea behind that. Let's continue the sketch of proof. So you have your sequence which almost satisfy a Lagrange condition. And now we would like to make a convergence. So if you know that the set of points that satisfy the Lagrange condition, so the set of critical points is compact, you can imagine that the set of almost critical points is compact. And if the almost is stated in terms of restricted thing, like which is less than delta, it's good. And your sequence of almost of points that satisfy almost the Lagrange equation will converge to something. And then that's good because you pass to the limit on the almost Euler-Lagrange equation. And you obtain an Euler-Lagrange equation at the limit. And that was what missed in the previous naive approach. We did not have the Euler-Lagrange equation in the limit. Okay. And then, okay, beta is smooth because of the Euler-Lagrange equation. So that's what I would like to apply. And I finally found the very adapted complete variational space for this problem. So, okay, it's technical and just specific to eigenvalues, so maybe I can go fast on these parts, but you take, in fact, the set of bilinear forms such that the function beta is smooth here, and you take the closure of this with respect to the norm of the bilinear form on H1. So X is the set of bilinear form of over H1 which are smooth in some sense. And you would like to have a complete space, so you take the closure. And this is adapted. So there are two reasons why it is adapted. The first one is because when you take a maximizing sequence of lambda 1, actually you know that it does not have points of concentration because of this argument there. But you know better. You know that, in fact, it is bounded in this space, in some sense. So this is the space that is adapted to maximizing sequences. And another property is that, okay, you want a very good Euler-Lagrange equation, in some sense. And here the Euler-Lagrange equation will be like phi squared minus 1 is something like the squared. So for technical reason, you just have an inequality, but it's something like the squared of a H1 function, which is small in H1. So it's somewhat better than being small in LP prime. It's small in H1. So, okay, it's because the Euler-Lagrange equation is adapted that I chose this space. So yes, you can generalize your first eigenfunction to this space. And I can go fast here. In fact, I need two conditions in order to formulate Euler-Lagrange equations. So in order to formulate Euler-Lagrange equation, I have to compute directional derivatives because of the definition of criticality. And the good way to compute this is to have these two assumptions. So the second one is natural. It's because you would like to have the existence of eigenfunctions. Your eigenvalue is defined as an infimum of something. So there is a variational thing that is hidden. And in order to have a convergence of minimizing sequence for this, you need a compact injection of LH1 into L2. And this is exactly the compact injection you want. And the first condition is something in order to have uniformity in the compact injection, for instance, and other things that guarantee to have this computation of the derivative of lambda 1, directional derivative of lambda 1. And then you can compute the criticality condition and so on. Okay, so I will not explain how the maximizing sequences which satisfy almost Euler-Lagrange equation converge. But it's just, in some sense, generalizing the compactness property of harmonic maps. So if you have a sequence of critical points which is compact, you can expect that a sequence of almost critical points is also compact. That's the philosophy of the thing. And that's what happens with this choice of the complete space. Okay, I don't know if I have time to do many other things. Okay, so maybe little words about the maximization over all the metrics. So once you have maximization on conformal classes, you just have to do maximization over all the conformal classes. But this is not so hard in some sense, because in some sense you do a maximization in the Teichmüller space, which is a finite dimensional space. So it's not like choosing a complete space which is complicated. And you can use the theory for the Teichmüller space. In fact, you take a maximizing sequence for lambda 1 of metrics. That is maximal in its conformal class. Then you obtain an equation, and that's very good to have an equation, as I told you before, because you want to pass to the limit on this equation, and you obtain that the limit satisfies the Lagrange equation. So here it's exactly what happens. You take Gn, a maximizing sequence which is maximal in its conformal class. And now we use the properties in dimension 2. In fact, in genus bigger than 2, Gn is a conformal factor times a hyperbolic metric. So I write this conformal factor because I recall that if I have a maximizer for this, then I have a sequence of harmonic maps that satisfy that the conformal factor is the density of energy of the harmonic map. So you can renormalize if you want. But it's, well, yeah, let's take it. So this is a maximizing sequence. The conformal factor here satisfy elliptic estimates when you do not have points of concentration, etc. But you can focus on the sequence of Hn, the sequence of a hyperbolic metric, which is the only thing that exists in the conformal class. And you can characterize non-compactness of Hn by the closed geodesics. So if you have a sequence of Hn such that the closed geodesic converge to 0, one closed geodesic converges to 0, then it's not compact. But well, in this theorem, the strict inequality is there in order to ensure compactness in some sense. And the same kind of argument as the one I did it. In some sense, when it is not compact, then you can have, for your hyperbolic metric, you can have collars with closed geodesic converging to 0 and collars like this. That's the two things that can happen here. Okay? And by test functions again, if you have collars like this, this means that you can have a thick part here and thick part here in order to have test functions like this and prove that lambda 1 goes to 0. So it's not possible. So you cannot have non-compactness in the sense that you have a collar that disconnects the surface. So the only collar that can happen in your description of a sequence of hyperbolic metric is this kind of loss of handle. So you lose topology, and this means that lambda 1 converges to the lambda 1 of lower topologies. But if you assume that the supremum over topology associated to gamma is bigger than the one associated to gamma minus 1, it's okay. So note that the large inequality was proved by Kolbo el-Soufi. And well, the large inequality is just taking a specific thing. You take something which is almost maximal for surfaces of genus gamma minus 1. You add an handle, which is small, You have a new metric that you can test in your problem for gamma. You pass to the limit. I mean, you test it, you have an inequality, and you pass to the limit, and you have the large inequality at the limit. So this large inequality is obvious in some sense. As soon as you have a theorem of convergence by topological perturbation of your surface, so it's a way to write just my drawing. You have a surface, you glue a cylinder, and you have that lambda 1 of your perturbative surface converges to lambda 1 of the surface. And what was difficult in this problem, so now I have to finish, so I will not go until the end, but it's okay, is to prove this strict inequality. So the first idea, it was the next slide, the first idea is to take this, a kind of sequence like this, and you have parameters that you can adjust. You can glue a cylinder which has specific geometry, the one you want, and you can glue it on the point you want, and so on. So you have choices, and the question could be, what is the choice of the handle you glue here in order to have that as epsilon goes to 0, this convergence is by this strict inequality. You are above the limit. So you can expect from such a result, okay, lambda 1 is written as an infimum, so you can expect that lambda 1 is reducing as epsilon is less than the limit as epsilon goes to 0, but you have the renormalized lambda 1 and you add some area, so you imagine that it compensates a little bit the thing. So it was the first question. And I talk about a naive approach. This approach does not work. I mean, it could work, but we did not succeed to do that. And the way to make it work is to use by an argument by induction that for the previous thing you have a maximizer, and it is a maximizer, and you attach something to this maximizer. And you use this. And well, I have to finish, but behind this is again hidden an argument with the use of Eklund variational principle. You take a maximizing sequence which resembles to this, and you make a perturbation of this by Eklund variational principle, and this gives you an argument by contradiction that proves that the equality cannot happen. So that's, I will finish here, and I thank you for your attention.